a special colloquium. It's an unusual time. It's Friday afternoon. Some of you maybe already go out for party. And today is a great honor to invite Professor Frank Cheng. Actually, his Chinese name is called Cheng Chou. It's very similar to my Chinese name because even all the square are the same numbers. And Professor Cheng is a world-renowned plasma physics, and then he made a seminal contribution to the field in the laboratory and space plasma. So Frank got a PhD from University of Iowa, then later got a position at the Princeton plasma lab until today. But actually, in between, he was invited by the government to come back to Taiwan to serve the chief scientist at the Space Preparation Center. And he also founded the Cheng, the Space and Plasma Center at the Cheng University. And due to his seminal contribution, he has been received several, actually many awards. Some of them is APS Physics Fellow, and also the APS Award for the outstanding contributing to plasma physics, and also the Chandrasekhar Award for his contribution. So today, Professor Cheng will share about his recent work as a very magnetic reconnection. So that's because it's such senior, but still published single author paper by himself. I saw that paper list. I said, oh gosh, it's more productive than the young people. That's very impressive. So that's welcome Professor Chen's talk.
Okay, thank you, Cheng, for the nice introductions. I remember more than maybe 10, 15 years ago, I was here once very briefly talking about, give a talk on the solar flares physics. But that time, not here, I don't know, maybe some other building. Yeah. But anyway, so today I would like to talk about this physics of magnetic reconnection that as you can see that this is mostly University of Tokyo group, and then this is a student of him, but then he already graduated for maybe 7, 8 years, and so he's at the QSD. QSD is the Fusion Research Center, the largest fusion Tokamak fusion center in Japan. And Professor Lucia and Sami, they need another fusion center. They are doing helical plasma device. So this work actually all day I was working in MHD physics since early 2000 because I have a postdoc. Actually, he did MHD simulation of flare, so I hired him to Princeton. And I always learn from young people, new people. To me, solar flare was that time was new to me because I was working mostly in fusion, magnetic Tokamak fusion physics. So then eventually Professor Ono, who is the leader of that group at Tokyo, he has several experimental devices that I will show. That he invited me to be a visiting professor at University of Tokyo 3 times. Each time is 1 year. So I had the honor to work with a very nice student, particularly this guy, Inoue-san. And then I kind of helped supervise the thesis and his work because he did mostly simulation, particle simulation work. And then eventually, I learned more experiment, and I tried discuss with them on what really been observed in the experimental result, and what does it mean from theoretical point of view. Okay, And so today I will start from here. I will talk about the concept of magnetic connection, and the most important is then I will explain the experimental result in University of Tokyo, and then I will introduce the MHD model. This three-part model and Paycheck model, they are the most fundamental MHD model of the magnetic reconnection physics. But then, after we did this particle in cell simulation, then we find it's a picture is totally different from the MHD model, and I will explain to you how it becomes different. Okay? And then, if I have time, then I will talk about introduce this flare, solar flare and magnetosphere magnetic reconnection phenomena. And okay, and so as I show you this show the movie again. I'm not getting the movie. Okay, I don't know how to, because there's a below there should be something. Yeah. Well, anyway, it's okay. We don't need that.
Sorry.
Okay.
Maybe.
Yeah, that's okay. So the most important concept of the MHD physics is this Ohm's law. Electric field and the plasma flow velocity cross B equals 0. This means that you can prove that from plasma physics that plasma is moving together with magnetic field. So it's called so-called frozen in conditions. So therefore, when plasma moves, magnetic field also move together. Okay. And so when this moves, then if we have say magnetic field from above, from this side that move down, and then this side that move up, okay, it requires the electric field to get this velocity movement. And so if you apply a uniform electric field out of plane, and then you have a magnetic field, say, you have equals B motion. So if you have a electric field moving out of plane, no more. So electric field goes this, and then magnetic field goes that way, magnetic field goes this way. Okay, so opposite magnetic field. Then this plasma and magnetic field will move down, and that will move up. Okay, and if they move up, this is called merging. They merge, and this is just a small region of that. And in fact, in general, this is a big area of plasma, and that big area of plasma on the top. Okay, and so they merge to each other, and with the opposite direction magnetic field. So what happened is this merging occur. Then if magnetic field does not reconnect, they just keep on accumulating. Eventually, magnetic field here, say uniform, and that magnetic field uniform, but they have opposite direction. Then you can prove that there's a current, very strong current. We call it current shift. Okay, so it will be going out. Okay, so that current shift becomes too big, eventually become infinite current, and that's a physics cannot be. Therefore, if you allow magnetic reconnect, this magnetic field and that magnetic field to reconnect, then after that, what happened? Previously, without reconnect, plasma can only stick in the field line, they move around the field line. Okay? But now, after reconnect, part of this field line and this field line forms this field line. Therefore, part of the plasma here and part of the plasma here, they can mix on the same field line. So this reconnection is not just magnetic field topology changes, but also allow plasma to mix from two different regions. Okay, so if you have this, say, low temperature and high temperature, then they get mixed. Okay, so then you have a very different plasma in here. Okay. So this is what I call change magnetic field topology, mix of the plasma. Okay, but in the meantime, although this reconnection field line only reconnecting at one point maybe or one line, then however the consequence is that the magnetic energy somehow pick up by this magnetic reconnection, the plasma energy pick up, and they pick up the magnetic energy. And how does it pick up the magnetic energy? It's actually the most critical issue that has to be solved. And so experimentally, we roughly know how because we have experimental result, we can draw the scaling. But theoretically, we don't know until my paper published 2021 was the first paper theoretically showed that it can how it scale with the magnetic field. Okay, so. Okay, so this is the device. That's okay. I can. It's a stick. Oh, here. There's a stick. Then I can use a stick. Stroker. So this is a University of Tokyo device. They go. It's a cylinder like this. And so if you turn this cylinder like this, okay, then it produces a plasma. Actually, say this is like a ring. It goes around like so. If you consider this is cylindrical coordinate, this is a ring in the toroidal angle. Okay, and so they produce another ring here, and this ring you can push this ring and that ring toward each other by using this control the current in the coil. Okay, and then as they push toward each other, then they can form the connection. If this magnetic field goes this way and that goes that way. Okay. So this should be this one shows up. Okay. Okay. See so this is the plasma that is the previous ring, and then you can see that. You can see it one more time. So after they merge, they form only one ring. Okay, one carbon ring. Okay. So original two ring comes down, and then we connect here. Okay, and then this, and then they form very quickly. So this is the real data. This is not the movie, not the intro. Yeah. So because they use many magnetic probe to measure the magnetic field. Okay. And so over the years they had many papers. I was a co-author of all their experimental paper, and I guess only early days, but actually they are very active group. So almost several papers for years.
Yeah. So Frank, when these two magnetic field merges, then the reconnection suddenly occurs, and
right.
Suddenly the entire field becomes
right.
Just
so it's a natural consequence, because if there's no reconnection, plasma will build up very strong current there, and they cannot mix the plasma.
But if I have the field line keep supplying to the merger,
that's okay. That's okay. Yeah. So this means that if you have a ring, you have a many field line in one ring, right? Another ring is a many field line. So say this one is many field line, and thrust, right? And then after they reconnect, this field line goes away. The next time this new field line comes in, and eventually exhaust. all the field lines, then they form in one unit. Okay. So one of the key results is that if you look at this reconnection region, they found that the ion is hot on the outer, we call it downstream, outflow side. Okay. Your problem come in and then flow out. Flow out this way and that way. Okay. So ion, and then but electron tends to get accelerated around this reconnection, reconnection area. Okay. So this is the electron temperature and this ion temperature measurement. So this is just a drawing. This is one of their devices called TS3U. So if you have a toroidal field go this way, and the toroidal field go this way, goes around this way, then this is going this direction, this one going the other direction. Therefore, when they merge, contact, they have opposite magnetic field. And then in this case, but you can also do this toroidal field. We have a toroidal field component going this way. Still, as long as one component is opposite, then it's okay. You can, but the heating rate, of course, is a little bit different. Okay, but here was moving too fast, so this one is a different time. Okay, so if you have early days, they start to reconnect, and then form one, right? And so on. And so they measure the ion temperature across this pole here. Then it hits up. Initially, the temperature is very low, but then eventually they become keV, 0.1 keV, and then 0.2 keV. And in this case, this experiment, the magnetic field is not so strong. Okay, maybe it's less than 1 kilodalton. Okay, so, but this is just Tokyo, University of Tokyo, but actually this experiment has been done by many places. In England, Curran Laboratory, they have a so-called mass device, and recent also in England is a company called Tokuma Energy. They have SD40, they call it SD40. So this is current, and then they over the year they have an experimental result. They measure the ion temperature changes because of the magnetic connection, and they come up with this story that the heating rate increase with this reconnection magnetic field square. So it goes with B squared. Here. And goes like B squared.
You said it's the temperature, but
temperature is a hard average energy.
Okay, average.
Yeah. Because it's not Australian. Okay. So and you can see that because all these data points, upstream plasma conditions are different, so it's spread all this. And then if you push the magnetic field higher, then eventually you get more energy here. Those 3 points are only very recent result in the last 2 or 3 years. Okay. So, and this is a simulation. Big simulation we also find very similar behavior of this. And so this is very encouraging because it's if you have 0.1 Tesla, then you can get this energy about 200 or 300 electron volt ion energy. But if you go to 1 Tesla, 0.1 Tesla, this is 1 Tesla, then you can get 10, 20 keV or something. Okay. So, therefore, this is a very efficient way of heating up the plasma. Okay. With this idea. And so I was when I came here, I talked with a few people, and then I said, oh, geez, how big is astrophysics plasma? If you have near neutron star, you can have maybe 10 to the 8 Tesla, okay? And if you have monitor, it's 10 to the 10, right? So let's just say, assuming that this experimental scaling can go all the way up to very high magnetic field. Then, let's say, it goes like 10 to the 10 Tesla, okay? Then the proton energy can go to 10 to the 24 eV, depends on your proton density, number density divided by experiment is roughly 10 to the 12 density, okay? So if you are this or even smaller, much less than this, so this total energy of proton can even higher. Okay, easy probably goes 10 to the 30. But of course, this is experimental result. Theory, I think, is also non-relativistic. When it goes to higher energy, we need to go to work on relativistic theory. Okay. So this is a hope that that we might be able to accelerate proton to very high energy that perhaps can explain the cosmic ray observation. Okay, because we know in cosmic ray there's lots of proton, right? So okay, so that is the result. And so what early days, how does people do the try to understand the result? Because this experimental result actually are new and different from the MHD theory. I mean, of course, MHD theory knows that they try to predict this outflow goes like a magnetic field. Goes like Ahun speed squared. And the Ahun speed is goes like B squared. Okay? But that's the flow energy. Not, who knows? I mean, as it flow through this, they go to downstream where there's a target, and then they can mix with the local plasma, higher density plasma, for example. Then they still get those energy. Okay? But so MHD, okay, MHD is a single fluid theory. We assume electron ion, they somehow move together. Okay, and so we provide. It only describe the center of mass, HD, center of mass, flow velocity, thermal pressure, and so on. Okay, ideal HD model or resistant HD model. But when we go to, we need to know how ion and electrons are heated or gain energy separately. Then in that case, yes.
So Frank is wondering about when the magnetic reconnection occurs, how much the magnetic energy, what's the fraction, will go to acceleration,
right?
And how much will remain on the B field, just coming out?
Okay.
What's the fraction about this?
This fraction is because the magnetic field continues to supply, okay, continue to supply. But at one instant time, how much energy, very short times, how much energy goes. The experimental shows that it can maybe 60% or 70% of magnetic energy. They can gain, I mean plasma can gain 60 to 70% of
very efficient.
Right. So let's start with this MHD model, because we have to understand how early days people think about this model. Okay. So, MHD is we have a mass density continuity equation and then charge neutrality. Okay, electron ion stick together, so there's no charge separation. And the momentum equation due to J cross E and the Brec force. Okay. And Ohm's law, E plus V cross B, we have a resistivity, assuming there's a resistivity. And this resistivity allows this field energy to dissipate. But if you use classical resistivity, it dissipates so slowly, it's impossible to explain this. Because this if we do simulation, it explains, I mean, it occurs in the cycles on time scale, electron cycles on time scale. Okay. So this reconnection process, very fast. And then you have a Maxwell equation here. Okay. So when was early days, this three-part model, because it's based on MHP, so electron ion move together. And so his main idea is that all plasma, if one to go from here upstream and downstream, go from upstream on both sides, go into downstream. They go through this region. We call it diffusion region. So they go through this region and they go up. And because there's a resistivity here, important. Outside there's a resistivity, but not so important, not important. So in here, eta times J, the current is high. So eta times J can be significant. Then the Brec important effect of dissipation. Then if they allow they do this assuming like this, you can go through the MHP theory. I don't show it here. I give a lecture on my graduate student lecture, plasma physics lecture. But anyway, most important is that if you want this outflow velocity to be order of the outflow speed of the inflow, use often is often speed squared equals B squared divided by a mass density n times m. Okay, and so you use the magnetic field at the upstream here to calculate this outflow speed and the density in the upstream to calculate. Okay, then you come up with the inflow speed. It's this. Goes like resistivity inside here, square root of that. Divided by L. L is the system size, is currency size, times V inflow outflow speed. And this number, this coefficient, is so small. Yeah, it's maybe 10 to the minus 5, 10 to the minus 6 for typical. So it's too slow. The inflow speed is too small. Observation, we know that inflow speed is roughly order of 0.1 of V outflow. Okay. Okay. So some people come up and say, okay, if we can make this resistivity anomalous, then maybe it's possible to speed up this. So actually I did. 20 years ago, we did simulation. We used anomalous resistivity and large resistivity to drive this. And indeed, it can fund very fast reconnection.
The friend in astrophysical system, large scale plasma, the resistivity should very small, more like an ideal MHP case.
Exactly. Yes.
Yeah. So, but I don't know how about the solar.
It's the same. So very small is we call it S number is 10 to the minus 10 to it's S is roughly one proportional to one number resistivity.
Yeah.
It's 10 to the 12, 10 to the 13, 14. But in astrophysics plasma could be even larger.
Yeah. So you use increase the resistance to infinity to boost the
right. You have to so therefore people still doing is that okay, let's assume that there are turbulent process inside here. Then if you can try many instability and resistivity means that the electron come in, they get kicked through. Classical is by collision. But if you have a turbulence, plasma goes electric field, magnetic field, they all get kicked around.
Oh, I see.
Yeah.
I see.
Then they enhance the resistivity.
Yeah.
Okay. So, but anyway, so this, but even you can increase the reconnection rate, you still don't know how plasma gains energy, for example, is still very too soon. Okay, so that is early days that people I mean, plasma physicists struggle with the sweep-Harker model. But then later, Princeton comes up. Princeton just passed away a few years ago. So. He said, he just proposed an idea, okay? And then he said that, okay, reconnected field line coming up, plasma come here, merge here.
Yeah.
He said, oh, okay, of course there's a reconnection.
Yeah.
The magnetic field reconnection. But he doesn't care how small his region is and so on, okay? In the previous paycheck, sweep-Harker model, you need a big area for plasma to stay inside to gain energy, okay? So you need a big current sheet. But here, he said, I don't care. He said, okay, so most plasma flows through here, through closed separate checks. This is a flow line, okay? And so he postulates that in the downstream, we call this region downstream region, that there is a pair of thermal shock wave. And shock front is at the top line here. Okay, so there are small shock here. Then when plasma comes in here, they get accelerated by the shock wave and change direction, get accelerated to large outflow velocity. Okay, that's a postulate, right? So later people come up with the theory that indeed this reconnection, inflow speed divided by inflow speed times sine kappa. Kappa is the angle of this separatrix line, okay? It's roughly between 1 and 1/2. And so then if this angle is not so small, okay, then say if this is 0.1, okay, then you can get this large, okay, right? So anyway, the then question is, have we ever seen this slow motion? So over the years, actually many people try to do MHC simulation. They hope to find this slow motion, and no one succeeded. Okay, and even observation, they have many satellite observation go to space, and they could not find a slow motion. They cannot. Some people claim they have, but no one can repeat it. Maybe. Okay. Yeah.
So, Frank, what exactly happened inside the very small point?
Nothing. He doesn't care. So he said, I don't care. Because all the action is all he wants to know is produce fast outflow.
So
fast inflow. That's all.
So the idea of just like reconnect or something happen at a very small scale, driven the shock wave, and the shock propose.
He did not explain how it's even either. Okay, just propose. In some sense, we know that the ion heating actually is inhibited both here and here. After we did this, the particle simulation, we found that, but it's totally different mechanism. Okay, that we know that it produced a potential wave, electrostatic field. That how upstream zero potential, this potential wave, and so there's a drop of the potential, and that potential is large enough that when ion goes come from here to into downstream region, they pick up energy. E times that potential drops. Okay, so that's my
your
theory.
theory.
Yeah.
Your theory.
But also our simulation.
So there's no current sheet at this point. No.
He has no currency, but we need a currency.
Yes.
Because we need to get a certain electron.
Potential. Yeah.
Right. And we also cannot just create potential drop here. Actually, potential drop across here. So part of the sweep Parker is correct. Part of tension is correct. Okay. Correct in the sense that where they gain energy, but the mechanism is wrong. Okay, it's different. Okay. So now, so it comes. So I actually was trained at the early days. When I was going, I trained in kinetic physics. So plasma, we have to treat plasma, electron, and ion separately. But later, I went to Princeton, and then I learned the MSc, and then I did many large-scale physics, Arturo physics, and so on. And eventually, I come back to the particle kinetic physics. Okay. So. One of the key point is that this current sheet here has to be order of ion gyro radius. That's the first thing. But this width in this direction. Okay. You have to push this plasma to ion gyro radius. Then you can fast reconnection occur, and then energy, all this what I described comes out. Okay. And so sweep Parker's this magnetic field structure is good. So we can, but other than the magnetic field structure, then we have to study how electron and ion dynamics in this kind of geometry.
But how about the width? Is that width matter for your case?
This?
Yes.
This is by nature, okay? So nature, some of them has very, very long in this direction. And some, so if you push the plasma, say, flow speed larger here and then here is smaller. But eventually, when we do simulation, we say this is the whole domain, this is a very large domain here. We initially push more flow velocity here, and eventually let the flow speed everywhere the same. So you are preferentially create a reconnection region out there. And you can do this by adjusting how you push. Because when plasma comes, some plasma here move fast, some plasma here move slow. Okay, so fast plasma move first.
But if the width is too large, then the reconnection rate will also drop.
Reconnection rate does not go with this. Okay, and in fact, the reconnection rate is more depends on the electric field, how much you push it. So in the electric field in the plasma, in each field line of plasma, there's electric field, and that electric field will move in the plasma, and eventually spread out. So initially, if you say only apply electric field here, and then eventually they come in. The field line carry the electric field together into this region. Okay. So let me just try. Okay, first give you rough idea what happened. Okay. So in this case, ion because it creates a potential well, yeah. So ion come here, they get energy. They come here, they get energy. So ion comes this way, comes here, comes in here. And electron come differently. Electron, they get accelerated into this region. And then they turn around, they come out, grow out. So the electron comes in. They are, of course, some of them come this way and they come out here. So that's therefore this electron ion flow pattern is different. Okay. And I just want to show you the simulation result first, maybe it's, because this is extruded from simulation result. Okay, this is the simulation, and these lines are the magnetic field line. And this electron flow velocity, this shows ion flow velocity, because in this simulation we only use a mass ratio 100. Okay. And so the arrow shows the flow speed. Okay. And there's also a velocity out of plane. That is we see is in color. But anyway, this and what this shows here is the reconnection electric field at the X point. One field line reconnect at the X point. Okay. So okay. So initially nothing, and then we push plasma comes in. Okay, and then it's eventually reconnected. And this is you can see electron has a large flow velocity here, but they also have small flow velocity going this way. And then here goes out, and here goes this way. Okay. And ion mostly comes in, and then they flow out. So, and at the steady state phase, let's say for this. This is the only there. Let's go. Okay, so this is okay. So this is the time, exactly this time. Yeah. The how many times this maybe 100 over 100 electron cycles on time. Already you see that this electron flow velocity L. And so some of them come this way, and then some come this way. And ion go this way. So then what happened is that the physics here is very important. We've got this part is correct. This is the red color is the electron that flow into this plane. And so this is, I'm sorry, because in this case electric field goes this way. And so electron can accelerate this way. So electron flow velocity is very large in this plane, out of plane. Okay. And yeah. And so anyway, so as I said that we roughly know even the particle distribution function and so on in here, in these simulations. And we know the electric field structures. So put a smaller scale, so it's better. So it's more like this electron. And it's too small to show up in this part. And ion is mostly flow this way.
So, Brian, I have a question. During this reconnection, the B field, the potential, how the geometry looks like? What is
this is B field, right? The field line. This is the flux, magnetic flux. So this means B field for this. Okay, so it is a B field. But there's an outer plane magnetic field I didn't show you. Okay. So this is a toroidal in this plane. The field line. This is exactly field line follow this line.
But I think you get the energy acceleration due to the, you also create electric field. Is that correct?
Yeah.
But how
so electric field, I will show you. There are two types of electric. One is electrostatic electric field. One is inductive electric field. And we can.
Is that in conclusion decoupling of electron and ion dynamics?
Yes.
Is that a general conclusion even for the case solar flare reconnection something?
Oh, of course. Yeah, this theory works for that. Yeah.
Okay. Okay.
Because it's a very fundamental process. Just two processes merge. Okay. What happened?
You mean that when the MHD doesn't work for expanding?
Part of simulation. This is big simulation.
Yeah, I know. Therefore, is it okay to say that the MHD simulation doesn't say anything?
No, of course it does not. MHD simulation cannot express this. So this is the electric field that distribution that comes in here with a current here. And this is the BG. BG is autoplane magnetic field. This is total B. This is parallel electric field. Okay, electric field is a E dot B divided by B. Right? So we found that there's a, we call it quasi-polar magnetic field, autoplane magnetic field. Okay, and this is very easy to understand because when electron comes in here, they get accelerated very fast by this EG electric field. This is almost uniform, EG uniform here. And then they get accelerated, they get as in collision, but then they get the V-cross B motion because the magnetic field, this magnetic field actually go like this. Then they flow out, they rotate the acceleration velocity out from Vg to V1. Okay. And so, and ion flow in here, but they're much slow because they're heavy mass. So their velocity is much smaller. And so electron velocity flow out here very fast. So this means that there's a current going this way, right? When you have a current going this way, then you have J cross B. I mean, J equals current, right? So you have this autoplane magnetic field going like this, and then here goes up. Okay. So that's kind of easy to explain. But once you have this magnetic field, then you create a parallel electric field, okay, because of the EG-BG, okay. But there's of course EXEY, but I will show you this. But so it creates the potential. So this is the electrostatic potential. And that potential here, there's a potential well. This is a red color here is a zero potential. Right? And so it's minus potential. Yeah. And so it produces a well, and here too. This well here is maybe about 30% difference. Then with this, you have electric field, right? Potential here is here's the law. So electrostatic field is minus gradient potential, right? Phi. And so you have electric field going in. Okay. Therefore, when ion move across here, they get accelerated by this electrostatic electric field into downstream. So that's the main reason that we calculate electric field, electrostatic electric field. Yeah. And it's accelerated mainly gain energy through this electric field, ion. But electron gain energies in here, okay, because they are being accelerated by this parallel electric field. And so this potential occurs because electrostatic potential, you need a charge separation, right? Without charge separation, if you have a Poisson equation, del square y equals minus 4 pi charge density, right? You have to create a charge density. So this is the charge density, Ni minus Ne. Okay? So this is a negative, this is positive here. So inside, and the here are here. So this is the approximation. So how do we explain all this? Okay. Yes.
So friend, the charge separation occurs due to the drift velocity.
No, I will explain that. Okay. So this is the exactly because of the current shift. Okay, structure. Okay. Okay. If you think of this, this is a switch direction. So this is X direction now. Okay. And so magnetic field, let's say this one pointing out. This magnetic field down here pointing in. Then eventually they go through zero, right? Change direction, right? From here to change to that direction. So this means current shift. Okay, this if you have this magnetic field direction, you will create a current in this direction. Okay. So I originally I was look at this field line. Now I'm tilting here. I'm looking at here. So when you have this, you know that electron particle gyrates around the magnetic field, right? And so outside here, I gyrate around with a magnetic field, electron, and here. But once they go into here, the anxiety changes. Because magnetic field becomes weak, and magnetic field equals zero here on this line. Therefore, if you have a particle, say, go here, and then they will turn around. When it comes to the different direction, so the particle moves like this. It's no longer in this region. It's no longer gyrating like this, okay, or like this, okay. But it's going this way. So this we call Mendelian orbit, and this means this the particle orbit become unmagnetized. So if you have an electric field along this direction, you can accelerate ion all the way to very, very long distance, okay, to gain a large energy. Therefore, this width, how big is this width? We have to understand, okay? And how do we calculate? But we roughly know this width is roughly under radius. Using the magnetic field here, local magnetic field to calculate. Okay? And now, ion and electron is different, right? Because electron mass is so small. Therefore, their Mendelian width region is much smaller than ion. Ion is this big. This electron is here. So electrons is magnetized outside on here. Therefore, if you put this one in here, say this is electron Mendelian width here, then outside ion electrons are magnetized. Their dynamics is different. They go through, if you have an electric field, it goes through equal speed driven motion. So because of this difference in this Mendelian width, and the particle dynamics are different for electron and ion, therefore they can create a charge separation. Okay, so that's want to know more yet to read. I know it's not so easy to see this. But therefore, all the particle acceleration has to be inside here, unless you have an electric field parallel to the magnetic field, right? If you have an electric field parallel to magnetic field, then you can keep on accelerating particle. Yes, please.
Do we assume the electron velocity, ion velocity the same?
No, they are different. Suppose they come in equal temperature, right? Or equal energy. then the velocity is different. I mean,
But they also
and the gyroid is also different.
Yeah.
Yeah, because
But the mass.
velocity goes like square root of mass, 1 over square root of mass, right? But the magnetic field goes like 1 over mass. So
That's different.
yeah,
Yes.
right.
Yeah.
So gyro radius is different.
Yeah. That's right.
So actually, therefore, this is a ratio that this is a membrane orbit width. It's roughly ion energy, ion mass divided by electron energy, electron mass to the 1/4 power. Okay, that ratio. So if you have a cell, if let's say come in the same energy, but mass is different, right? So proton is 1800 times. So 1/4 of that is how much? 7, 8, right? Okay. So this means 7 or 8 times of that. So you have enough space to create, allow charge separation to build up. Okay. Now, if you have an electron positron pair, then we say, right? However, if you have a different energy, then it might be able to create. So this electrostatic potential, this difference between the membrane width may not be occurring, or may be not so strong in the electron positron pair plasma. Okay. But anyway, so with all this, actually, I want to dig out what happened to the simulation result. Okay, so in the simulation, we had the flow structure on this everywhere, but then we can, my theory was done in this region. Okay. But then we can calculate the velocity along this direction, velocity along this direction. Okay. So I draw this directions here. So this is in the y direction, this is inflow direction, and we have electron ion velocity as function of y. So this y greater than 0 is from above, y below 0 is from below. And electron flow velocity, inflow velocity is different, right? And their g velocity, accelerated velocity. Electron gains big acceleration velocity inside here. And this region, this LMI is here, this is ion membrane width. LME is here, electron membrane width. So this is mostly accelerated here, but then there gets a pre-acceleration somewhere by because of the electrification across the drift in the outer plane direction, G direction. So this is roughly we know how it is. And then we can calculate the charge. And then this blue line is the electron, ion is the yellow line, and then there's create a charge separation. Okay. And then those are the current Bx, By, and then Bg. Okay, Bg. Bg is this one. And potential, you can form the potential where. Outside is 0, and electric field, and the charge separation. So we roughly know how this, and then we get the structure in the x direction also, for this velocity. So one of the very important is that this outflow velocity of electron inside the current sheet here, right? It's linear. Okay, it's almost linear, right? And the ion, same thing, almost linear inside the ion. And However, the other VY almost constant, uniform, almost. Okay, VZ almost different level. Different Y. This is different Y, and then X, almost uniform. So with all this parameter and also potential, we can come up with a theory, and we can calculate the theory. We can use a theory, analytic theory, to come up with some analytic solution. Therefore, we assume some velocity profile of ion, say ion extraction, outflow, and then inflow VIY. And we know this is magnetized, this inside unmagnetized. So we know that the velocity goes like this. Then we can also assume the electron, same thing, okay? Very similar. But then we can come up with solution in different regions, and then all this are easy to solve. Okay, so this is in the region between ion membrane and electron membrane width. This is inside the membrane width region. So what will happen here? And then we can solve the solution. And if we cannot solve, then we can do a numerical, because the second order we can integrate those equations and match the solution. So then we can assume many different velocity profile and do simulation, do theory, theoretical numerical calculations. Right? Oh, and some of the results like this. So these are the parameters of the current profile, amplitude, and so on. Then you have the ion, electron density, and so on. Okay, and then from that, then you can calculate almost every classical quantity that we want to calculate from plasma physics, right? Okay, and then most important, we can calculate the potential. How much the potential drops? Okay, and this is normalized. So, and the definition of this YP is this one. B squared over 4 pi a times E. Okay. We know what that means, okay, later. This is B0, right? But then 5B is there are times B0. So it becomes B0 squared divided by 4 pi N times E. So we can try many different, okay, theoretically. Then we come up with this. Let me show you. One of the why I choose this parameter, because I did further simplification. I found out this is the most important parameter. Therefore, I calculate, for example, the potential drops here. Then all this stuff with a different current profile and so on, okay? And therefore, with different variation of this parameter, look like this. And I actually did an analytic theory that further simplified this inflow current profile, flow profile. Then I come up with this analytic theory like this. Then I put the peak simulation result right up here, because we only did one case. The one is important. It takes many days, and then you have to analyze data carefully. Okay? So therefore, this my simplified solution, analytical solution, it's not too bad. It's it provides almost an upper bound on the compares all the possible inflow profile. Okay, and also. So, for example, like this, maybe 20-30% difference. Okay, which as a theory I'm happy. Even factor 2 I'm happy. Okay, right? So I come up with this analytical theory. I come up, compare with a numerical solution.
Sorry, can you explain what's the SE here? You define
Which one?
SE.
SE is this parameter is the relative one, is the acceleration. How much acceleration velocity of that can get inside the current sheet. So it depends on the how big the current sheet, right? So if current sheet is very long, then particle in there stay a long time, and then they keep on accelerating, accelerate. So can accelerate to very high energy. Okay. So let me see this. I did. Yeah. So this SE is is 1 plus the electron get acceleration by the conventional electric field inside the electron mingled with, and times the time, because time depends on how long the current sheet. So the electron can stay inside the current sheet. So if you have very long current sheet, this time is very long. And there's we decide velocity is the electron, the equal speed velocity is it comes into the electron mingling with the edge, and then they come in. So once they come in, they get accelerated. So I left this as a free parameter because I want to allow the current sheet to be very arbitrary. Therefore, as a parameter, so my theory is that allow this to be a parameter. I can. By the way, this is published in the paper. So this analytical solution is by assuming this effect is not so important. This part of the inflow, the Vx is not so important. And then also, because originally it comes with this. So, but I said, okay, let's just a constant flow velocity here in the Vx. With these two assumptions, then all the solutions become solvable analytically. And then now it's all algebraic, right? And but I simplify solution and so on. So with this kind of assumption, I got the solution like this, which is not too much different from I do the maybe more realistic flow profile. Okay. And then most important is that we can get the formula, analytical formula over this. Everything, the potential dropped. Okay, it's depends on this parameter, and this is goes like this. It's only determined SLME divided by delta, mostly like this. So this is analytical theory, and then all electric field, how big the electric field I get, how big the electric potential, all this stuff, and how big the magnetic field. It's all solved, okay, analytically, and depends mainly on this parameter, SE. Mainly depend on this parameter. But of course, it all depends on this. So, and allow this one to be, if I don't even care how big it is, I lump into one parameter. So, Now, with this analytical solution, we can get analytical expression of the potential drop, where the ion gains energy, right? So then ion potential drop goes like this. Okay, so the ion will get energy, and then if you write this like this, it goes like B squared divided by 4 pi n times this parameter. And this parameter can depend on your actual. So experimentally, there's a spread. But the most important is that this factor comes out. Okay. So and then if this varies within 10, it's okay. Right? Depends on upstream parameter, plasma conditions. And so now, what is 5B means? 5B equals omega C divided by omega P squared times this electron rest mass energy. Okay, so E5 is like that. And in astrophysical plasma, this guy is very large. Okay, much bigger than 1. It's your sigma, right? So this is huge. And so the solution comes out this potential here like this. So it's a few times of that. But this can be less than 1, so I don't know. Yeah. So that's what's important, that we are allowed to explain the scaling. Why it goes like B squared. Okay. So this in the experiment. Yeah. So why it goes like, actually goes like B squared divided by n. But in this experiment, the n cannot change too much. In the early days, but they can have a higher thing. Yes.
Well, I am naive thinking about this relation. Can I think about the energy gained by the ion or photon was from the magnetic energy could have been recombined and
converted into the electrostatic energy.
Yes.
Potential.
Yes.
Yeah.
And but in that energy, think about it in terms of magnetic field energy is B squared. Yeah. So I can get this relation by this kind of B squared amount of energy convert into the electrostatic energy.
Right.
Yeah.
So this B squared energy, as I say, is proportional, but experimentally, roughly 60%, 50,
Yes,
60%
conversion.
Yeah. Okay, so I did not explain the electron. Actually, electron can gain even more energy. Okay, in the current sheet, by reconnected by this. Yeah. So it turned out that electron also scale with B squared times this factor SEVG.
It's squared.
Yeah. And so that is
Much more.
therefore, if you have very long current, it can accelerate even more higher energy. Okay. So, but remember, the amount of particle, the electron come into the current, reconnection collision is small. Because maybe it goes across into the downstream, across the separate tracks going to downstream. Okay? Because field line cannot go in. They move with the field line and go in. Okay? So this number of particles, even though they get very high energy, but number is small compared with total. So that's why after they get energy, they move to downstream. They form a high energy tail of this. So that's why most of the electron accelerate energy in the reconnection process, like in solar flare, those accelerated electrons are form a tail. Okay, high energy tail. Maybe two tail. Who knows? Depends on energy spectrum. Okay. Yeah. So then you can combine energy. You have to mix total energy. Downstream is original. I mean the plasma that don't get. I mean energy. They actually lose energy by the electrostatic potential as they move across separate sheet into downstream. They lose energy by that. Okay, but they gain energy because of the mix with the high energy tail that comes into to the downstream. So, okay, let me show you the in the space physics. This is the Earth, and this is a solar wind. And so a solar wind impinges on the Earth's magnetosphere. Earth right now, magnetosphere goes from south to north. So if you have a solar wind plus magnetic field that goes north to south, then you can have a reconnection here. Right? There are two regions that we connect. One is tail, but I don't want to get it. But there's the data person actually showed this. Yeah. They have the ion temperature, of course, we know it's roughly, it goes like B squared. Okay. They also find electron temperature also goes like B squared. But coefficient is much smaller. It's only, let's say, ion temperature. This is a small average energy. So electron and ion, the coefficient is magic number 7. AI divided by AE is 7 times. Okay, so I don't know. So this is published right there. In solar flare, this is a measurement by several satellites, goes and the racing and the wind, and then it's a particle. Wind 3D, P is the particle detector. But all these satellites are very near Earth, very far from. And so they measure this flux because Reiki is from Berkeley satellite, and it's an X-ray telescope. So they measure that X-ray the photon, and so they measure this photon flux like this. So a function of time by Reiki satellite, and then they have a very impulsive acceleration of the particle. Because even though this is a photon, but it indicates that electron is being accelerated very fast, and then decay. So, and indeed, the wind 3D is a wind satellite. Measure the particle flux later. Okay. So several hours later, I guess. Let's see. 30 minutes later. Okay. And so then they come up this from the X-ray emissions. Okay, so because they don't measure the low emissions, they measure the X-ray. So few kV all the way to 100 kV, and so they get this. Okay, and this is the particle flux measured by the electron by the wind spacecraft. So anyway, so and now from other study we know that reconnection play important role in this solar flare issues. Okay, so already more than 1 hour, right? We stop here. Sorry. Okay, thank you.
Your question?
Mm.
Yeah, anyway, so my understanding about magnetic recursion is that turbines is most important. And, however, what you say is not the case.
No.
And I understand what you want to say. However, is that applicable to any case of the magnetic recursion or under some restricted conditions?
This theory, as long as a collisionless plasma, it has to go.
Collisionless plasma?
Right.
No, most of the plasma in the universe.
Yeah, yeah. Because we are doing purely exactly collisionless.
Mm-hmm. Oh, you mean it is not necessary to think about the turbines?
No.
Is that
I should not say no turbulence. In the simulation, we found turbulence, but I am trying to pick up the most dominant physics. Okay. Turbulence plays secondary role.
Okay. I see.
Yeah.
I see.
And so, as a theorist, as a physicist, we pick up the
Yes. Yeah, I
say
understand.
80%, 90%.
Yeah, I understand. What you
And
say.
then we worry about that
Yeah.
10% later.
Okay. Okay.
Yeah.
So I was wondering, the turbulence might play a more important role in terms of the rate.
In terms of maybe 3D, because this simulation is 2.5D, 2D.
Yeah.
But I can tell you, experiment. Experiment is 3D.
Yeah.
Turbulence is not so important. That's why this theory can explain the experimental result. Yes, please.
So I have two questions. So first, is your theoretical result relativistic or non-relativistic?
Non-relativistic. Yeah.
Okay. So the second one is that you have mentioned one key parameter, which is the resistivity in earlier of the talk, but not in the later half. So what happened? Is that not important, or is that something?
No. Relativistic change the particle orbit and so on.
It's important.
It's important. It's so that's why. But if just from extrapolation from the classical, okay, what I'm saying that is already clear. Yeah. From this extrapolation already few numbers. This
This is so very
too big.
Huge. It's too huge.
Too big.
It's way for the cosmic ray.
Right. And so we need the relativistic theory to
You need to
correct
some correction time.
Yeah.
I think
But
you
I
need.
think you have a resistivity estimate based on your theory.
Theory has a resistivity, yes, because we know the current,
Right.
and you just use MHD formulation.
And what's the
E plus V cross B equals eta J, right?
Yeah.
And so we calculate the current, we calculate the electric field, EG electric field, right? We know. Then it's I have that the theory predict that anomalous resistivity from simulation. I mean from this simulation result, from this theory.
what's the order of magnitude roughly?
Here. So resistivity is E divided by J, right? So with our theory, it goes like this. It depends on the reconnection electric field. And there's SE parameter here, and then divided by B0. B0 is outside before it comes into reconnect the upstream magnetic field times omega C divided by omega PE squared. I can put omega C divided by omega C here, right? Multiple times divided by omega C. And this number is should be much larger than classical because I expect the ratio of that. Okay. I think this, because this is the classical coefficient, this is omega PD. This is much bigger than this. And in the astrophysical plasma, I don't know how big is this easy electric field compared with the magnetic field that comes in to the connection layer. So that depends on how fast you push the plasma. So in the experiment, typically 0.1 or less. This number. But this is all the 1 maybe all the 1.6. So square root of that is so mostly it's because this omega p over b.
So Frank, there's one comment I want to make. Also question about turbulence flow. The key thing is inductory plasma. This kind of experience actually, due to the dynamic dimension, the Reynolds numbers compared with astrophysical plasma is very different. So usually turbulence everywhere in the astrophysical phenomena, which is not easy to be seen in the lab because it's a few meters. But we are talking about parsec, AU scale, so it's not.
So even this curve shape, width is iota radius, which could be very small. Okay, but the process allows you to convert this magnetic energy into the particle energy. Because it creates this potential.
But I see very intrinsic property. The beautiful point about this theory is about you can calculate the different sort of gain radius of the ion and electron. That can explain about some of the.
That's why we need analytical theory, analytical solutions, simplify analytical solutions.